Hi, here we have a problem from the ULB book where we want to solve this circuit and actually design it to give us a value for C that's going to give us the fastest smooth response. So in this, remember that the underdamped is going to give you a lot of oscillations. That's definitely not going to be the smoothest one. For the overdamped, it's going to be a slower response, and then for the fastest, smoothest response, it's going to be critically damped. So critically damped, we want to have our roots to be two of the same value. So the characteristic equation, you can solve this first by doing, you can go back and watch the other video where I find it with the transfer function. From that transfer function, you can then take those variables. The other option is just to use the table that already has solved this. And so the table shows us that we need to determine if it's in a parallel or series. So we see and look at the final circuit and the location of the capacitor and inductor to each other. So here with this closed, you can see that this is going to be a parallel form. So here we have a parallel circuit of LC, and so we can find alpha, which is 1 over 2 the RTHC. So our RTH we find with the final circuit. So in this case, it's going to be the switch is closed. We're going to put our A and B is going to be this side A and this side B. And then we remove the sources for a resistance equivalence. And so these two in parallel is going to give us 6 ohms, or 1 over 6 plus 1 over 6 is 3. And so we have 8 in parallel with 3 is our pathway, because going from A, we're going to split and go through 2 different pathways to get back to B. So that's going to be a parallel form. So our RTH is going to be 8 in parallel with 3, which gives me 1 over 3 plus 1 over 8. Getting a common denominator gives me 8 plus 3 over 24. And then we flip that to give me 24 over 11. So our RTH will be 24 over 11. And so this gives me alpha is 1 over 2, and then 24 over 11 can be flipped, and then C. And then omega naught is 1 over the square root of LC. And so L is 5 milli, so 10 to the minus 3. C, and we can equate these two for critically damped. So remember that critically damped is when alpha is equal to omega naught. So we can also do that by solving for the roots of the system here, and you're going to see again, you're going to get that in order to get this to be double roots, the L or the C has to be equal to each other, and you'll get the same equations either way. So you can use that as an exercise if you want to go back and solve it with the S-domain method and then equate those. So solving this, we get 11 over 2 times 24 times C, and that's going to be equal to 1 over the square root. So we're going to square each side to get rid of the square root. And then we're going to solve for C. So you're going to get C's on one side and the constants on the other side. So using algebra, you're going to end up with 5 times 10 to the minus 3 over 4 times 24 over 11 squared. And so this ends up giving a 0.26 millifarad. So this would be the value of C that we would want. So to find now, we want to find IL of t. So to do that, we're going to need to use the table, or again, we can go back to the S equation and then we can solve the S equation, the frequency domain transfer function equation. So we could go back and solve this one, put it in its factored form, and then use the table to translate it back into the time domain. Here we can use the table to find IL of t by finding the initial and the final conditions. And so either method, you're going to get the same answer. So I encourage you to do them both ways and then see that they do equal each other. So in t equals 0 minus stage, you're going to have the switch is going to be open, which you can hopefully see here that you then have 0 voltage. So you're going to have 0 voltage here with the switch open, and then here you're going to have 9. So the current's going to go this way too. So it's going to be 9 divided by 3. Remember, this was 6 in parallel with 6. So it's a 3 ohm equivalent. So we get 3 amps. And then when we switch, we're going to get the same values for the current. So IL of 0 plus has to stay the same. So that will stay 3 amps. And then our VC of 0 minus and 0 plus has to stay the same. So those equal 0. And then I need to know what VL of 0, which is going to be at 0 plus, is going to be. So when you switch it to 0 plus, you're going to note that it's going to be in parallel. So this is going to be a current source that has 3 amps. And this is going to be a voltage source of 0 volts, which is going to make it look like a short. So VL is going to be across this, so you can see that VL is going to be the same as VC, which will be 0 volts. So that one will be our initial value for VL of 0 will be 0. IL of 0 is 3. And then we need to find the final circuit. And so the final stage, we're going to get, the switch will be closed, and now these are going to be a wire and an open. So a wire for your inductor, and then this is going to be open for your voltage. So to find IL here, you can see that it shorts the 8 ohm resistor. So again, we're going to get that IL infinity is that 9 over 3. Again, these equivalents is 3 ohms. And then this is going to be, the current's going to still go that same direction to follow the direction of the IL labeling. So this is going to be 3 amps again. So this going to 3, you're going to get 0 for both of these. So 0 and 0, which makes this easy because then you just have IL. So these are both zeros, so then you get IL, which is equal to 3. So IL of t ends up just being 3. for your answer here. All right, thanks for watching.